In this video, we are once again going to apply the theorem that is WNC equals MEF minus MEI to figure out the speed with which the block M will drop, okay, or rather the speed that the block M1 has when it falls a height h. Now, what's happening in the problem is that M1 is connected to M2 by a light and inextensible string. M2 is on an incline, and now there's also friction. So we have to encounter a lot of forces, and we'll see that by using this theorem, we can really simplify the problem. Although one must keep in mind that you have a lot of components that you need to keep in mind. So let's do this very carefully, and as we go along, pay attention to a lot of details. The first of which is that in the beginning, M1 is the only thing that will have energy, and we'll show that. Okay, M2 in the beginning has no energy because M2 is going to go up, M1 is going to go down, which means that we can assume where M2 is in the beginning to be the 0 for its height, and then we can measure all heights from there for M2. For M1, it's very easy. We can measure the height for M1 relative to the lowest point. Relative to its lowest point, M2 is, on the other hand, is going to go up, M1 is going to go down. Okay, now again notice that the height gain for M2 is not simply h. Okay, I hope that by now you have learned to realize that you need to figure out the height gain. Draw a simple triangle here. This angle is theta, and the height gain for M2 is simply h times sine of theta. This should be standard by now. So this allows us to deal with all the components, and then friction, dealing with the work done by friction, is again going to be simple and straightforward. Keep in mind again that the contact force is equal to m2g cosine theta, and then life is good. Okay, so let's proceed. Let's go ahead and let's find all the components for this. Let's begin by finding MEI. Now, since I have two objects, my total MEI is going to be equal to ME1 plus ME2 multiplied by the initial mechanicals for both. Now, let's write down the mechanical energy for mass 1. In the beginning, it is not moving, so that's 0 kinetic. In the beginning, M1 is at its highest point, so it definitely has gravitational potential energy, which will simply be M1 GH. So this is all for the block 1. On the other hand, for block 2, it is not moving as well in the beginning, so 0 kinetic. Also, block 2 is at its lowest point, 0 potential. So you see that the mechanical energy is very easily M1GH. Life is good. Now, let us find the mechanical energy at the end. Now you realize that at once they both move to height h, they're both moving. Since they're connected by a light and inextensible string, they both have the same speeds. So they'll both have kinetic energies, but only one of them will have potential energy that we need to worry about. So let's write down everything for M1. M1 has kinetic energy, 1/2 mv squared. This v is what we're looking at for, plus 0 for its potential, plus for the block 2, it has 1/2 times m2 times v squared plus m2g times h sine theta. Remember once again that the height gained by the block on the incline is h sine theta, and it's not simply equal to h. So that's a common mistake that people make. So try to make sure that you don't make that mistake. Alright, so we have all our components, or rather we have the mechanical energies. Let us now obtain the work done. Now, work done by friction is very simple. Okay, we need to know the force of friction, which happens to be the coefficient of friction mu k times Fn, and Fn in this case is simply equal to m2g times cosine of theta. So this is my friction. It travels out distance h, and the angle that the force of friction makes with the displacement is 180 degrees, which is what makes it minus. So this will give me negative mu k m2g cosine theta times h. Great. We have all our components. And now we can plug it into the equation. We get mu k, negative mu k m2g cosine theta times h equals the initial mechanical, the final mechanical is equal to 1/2 m1v squared plus 1/2 m2v squared plus m2gh sine theta minus the initial mechanical, which is equal to simply m1gh. Now we are ready to solve this. Let's move all the terms other than the v's to the left hand side, which means we're going to take all these guys and move them here, and what we're going to end up getting is m1gh minus m2gh sine theta minus mu k m2gh cosine theta equals 1/2 m1 plus m2 times v squared, and this gives me v, as v squared equals, we can actually factor out the g and the h, and we have m1 minus m2 minus mu k times m2. No, you know what? Made a mistake here. m1 minus m2 sine theta minus mu k m2 cosine theta times gh. Multiply this by 2, divide this by m1 plus m2, and you know what, let me also skip a step and take the square root right here so that I don't have to write the whole thing again. Great, so that's your answer.